Yeah, having a look before to what you have been seeing in the during the week and today, I think this one is going to be really relaxing, and there is no math. It's just I just want to talk to you about a bit of high performance computing with Python, which is just very loose concept, but yeah, let's see. So HPC with Python, high performance computing with Python is it's called. Sorry, let me just move some. Yeah, everything that has to do with doing numerical computation with Python, and yeah, Python. Now it's very common to see it everywhere. Is everywhere in deep learning and even in also fluid dynamics and weird things that a few years ago I don't know, Python was like really Python, no, but yeah, now it's everywhere, and I think most of the more important reasons to me why that's the case is well, everybody likes Python. Python is really nice to work with, very user friendly, but also Python is very easy to customize every functionality. You can make like domain language or almost language very easily with Python, like you see with TensorFlow, that you change a lot the functionality and it doesn't look even like Python anymore. And the other thing, I guess the most important, is that it's really easy to make it to bind it to HPC traditional languages like Fortran and C. And in fact, just a Python in HPC Python program is just some Python thread that is going to call for the, let's say, the heavy lifting, the numerical calculations. It will call C code or Fortran code, and then this code is going to execute, and then the Python program is going to continue, and something else of C is going to be computed, and then they can be processes or threads. Things like that. So in practice, you are just running C whilst having fun with Python. So you interact with the Python-like API, but you are actually running C code, which is how you can take advantage of this big infrastructures like the clusters in the National Supercomputer Center. And in HPC, the Python appears in, I think, in my opinion, in these three different ways. One is all the NumPy-like packages that are done for operations with multidimensional arrays, and that's the case of NumPy, of course, and many other applications that they re-implement NumPy for different. To support different platforms, for instance, like CuPy, which is just a complete implementation of the NumPy API to run on GPUs. Initially, it was just for NVIDIA GPUs, but now you can see it also in AMD GPUs working with ROCm. And there is also PyTorch and TensorFlow and JAX and so on, that they are mostly used in deep learning, because besides having all this functionality to do operations with large matrices, they have complete APIs dedicated just for neural network training and everything, actually serving and everything. This is very nice that all these packages, they kind of follow the same idea of NumPy, because for once you know one, it's easy to move to the other ones. But in cases like NumPy and CuPy, they can be used as backend for other packages, higher level packages that used to use NumPy only as a backend. Now you can easily change it, and since the API is the same, you can put these programs to run in GPUs without having to change your code. So this is the first group, NumPy-like packages. The second one is compile code. That compile code that can be things like Numba and Python that we're going to see a bit later. The idea is that you write Python code, and with the help of generate some decorators or some particular syntax, you can generate code, and this code is compiled. And now you're not going to be running Python code anymore, but instead just machine code that it can be Python. It's just C code, but Numba is it's not really. It's based on LLVM compilers and just one particular set of compilers. And that one, of course, compared to Python, that is an interpreted language, it offers just very good improve in performance. There is one in this category that is called Tai-Chi Lang, that I think is rather new, or at least I know it not so long ago, that it has many functionalities for fluid dynamics and for solid fluids, and also for visualization of really large data sets in 3D and things like that. You can have a look. And also PyTorch and TensorFlow, somehow they can be in that category, because PyTorch, for one, it provides this jitter, I think it's called. This is just-in-time compilation option to create compiled code, and same for TensorFlow. I don't know if they are so as general as Numba, but it's just another way of running these programs. Okay, and like that. The idea with all of them is that you don't have to learn. You don't have to learn C and again Fortran, things like that to do really performant to write really performant code. And right now, many of them, I guess, except Python, all of the rest, they provide support for GPUs and CPUs. And in this category, it's not really C, but it's very common to write part of your Python packages or the code that you're writing in Python to write it in C, and a bit less common in Fortran 90, but there is also the possibility. And there are a few packages to make that very simple. One is F2Py that comes with NumPy. It's an executable, and that it allows to write Fortran. So if you have Fortran 90 code, you can create wrappers for it, and it works in a very strange way. Well, not strange, but anyway, the idea is that you have Fortran code, and it will take your code and add a lot of code in your code, and then it will get C. It will write a C wrapper to call your code from Fortran, and it will from this C wrapper is going to create a wrapper for Python. So there are like many languages in between, but the idea is that even if you don't know Fortran 90, sometimes there are things that are very hard to write in Python, and sometimes maybe they are easier in Fortran 90 if you are into that. And just by running an executable, you can just create a wrapper for Python. I have some examples. If someone is interested in this, we can discuss later, but I didn't include it.
Can I ask you something?
Yeah, sure.
What is the easiest thing to write the wrapper for C or C++? I use sometimes iBind 11, I don't have people in C.
I like more this one, CFFI. That this is something similar. Also, the idea is that you put the code and you read it so you kind of read it inside of Python and pass it to some CFFI object, and basically you say compile, and it will do everything for you. And it also has the functionalities of compiling. So you give code, or you can give libraries. If you have a library that you don't know the code, but you know the API, how to use it, you can just wrap it without having the code, which is really, really useful. Okay, and this one, of course, if you write, if you're a developer of a package like PyTorch or TensorFlow or NumPy or anything of this, yeah, you will be all the time using this, this kind of Python. Yes. Okay. And yeah, the last part is what has to do with scaling to clusters, just because NumPy and Numba and the things that I mentioned now, they are just for a single computer. And here in scaling, there are software like Dask and PySpark and MPI4Py. And this one, Econometrics, that is it's not very popular, but is sort of a NumPy natively for clusters. It's made by NVIDIA. And the idea is that these ones, they provide schedulers in the backend, so your job can run in your laptop, and then you can take it to a big cluster and you can run it as well there without having to change the code, or at least not so much. And my idea for today is just to select like one example of each and tell you how to approach working with these packages. I mean, in a very high level, but at least if it is new to you, you know where to look at afterwards. And yeah, we're going to start with NumPy. And NumPy, probably all of you know it and are familiar with it, because it's like the first stop in Python if you want to do anything numerical. Yeah, NumPy is the library that like the first library that bring the numerical support in NumPy. And the idea is that it has multidimensional array object that is written in C, and NumPy brings a bunch of functionalities to work with these arrays. And then you can find linear algebra stuff, Fourier transform, a lot of random number capabilities that we use a lot always to prototype. And it brings this utility F2Py to write Fortran code, and it's compatible with C, which means that when you use one of these packages for wrapping code in C, you can very easily change NumPy objects from C or operate on C created objects in some data in NumPy. And again, there are many libraries that implement NumPy for different platforms and different use. So, again, CuPy, that is just a NumPy implementation for GPUs. And there is Dask, that we will see later, that has a NumPy implementation for working in clusters for scaling. And so one of these examples that I have mentioned in CuPy is, you know what is it already, I've said it many times. But besides having just NumPy, it has many backends to do calculations on the GPUs, and those are done by NVIDIA libraries and corresponding ROCm for AMD. Libraries like cuBLAS, cuDNN, which is used for convolutions in neural networks.
So, can you here go a bit slow, so we're not, flow for fast in the room? It's cool down. So like.
Okay, sorry.
So cuBLAS is essentially dense linear algebra. So vector, matrix, vector, matrix, vector, matrix. Then sorry.
Sorry. Yeah, thank you. Sorry. Yeah, the idea is same as NumPy. All these functionalities written in C, they use as backend libraries that already exist. And in NumPy, very popular are BLAS or equivalent implementation of BLAS, which BLAS, I don't know what B means, but basic. Okay, LA is linear algebra. Thank you. And S? Subroutines. Oh, okay, thanks. So, and then, yeah, anytime that you do anything with the linear algebra in NumPy, it will use BLAS or another version of the BLAS API. And NVIDIA has like corresponding libraries for GPUs. That would be cuBLAS, which means CUDA BLAS. And then there is cuDNN, which is the backend that is using PyTorch and TensorFlow for convolution operations. And current random numbers. This is solvers for, I guess, for differential equations, I suppose. And yeah, sparse support FFT, and NCCL is a library for communication in clusters, GPU to GPU. Okay, and through CuPy, you have access to all that using the NumPy API that you already know, or yeah, and you need a GPU.
Only works with NVIDIA GPU?
No, it also used for AMD. Yeah. Works for AMD. Yeah. And yeah, since we don't have a GPU, I'm not going to show it, but I could show it later if someone is interested in another computer. It's fine. Yeah.
Can you say it like it's a drop-in replacement? I mean, would it make sense sort of to use the one, use the other, sort of use both, or like?
So if you have something like it can take advantage of the GPU and you already have it written in NumPy, this is just for CPU code, then it's as simple as you just change, instead of import NumPy, you put import CuPy, and then you run it, and it will automatically run on the GPU. So there is no.
You import CuPy as AMP. So if you code this like AMP or whatever.
Yeah. It has something a bit smarter that is you can create. Let's say that you have a library of different functions, and it has a functionality to guess which package is the data coming from. If it is NumPy, it has something that say, okay, do it with NumPy. But if you pass something that is in the GPU, that is CuPy, it will say, okay, run it on the GPU. And yeah, and all the data transfer between GPU and host, this is also taken care. I mean, it's really user friendly, so it's NumPy on the GPU. Yeah, and yeah, SciPy, just to finish with all these packages, is just an extension of NumPy, and I don't think CuPy goes just beyond the NumPy API to support all the functionalities of SciPy. But anyway, it's something that is always very used, NumPy and SciPy just together. It's just a complement. And yeah. And okay, so enough with the packages. So the idea with NumPy, as I mentioned before, is to work with large multidimensional arrays, and the code is written. I mean, NumPy is written in a way that is meant to be used through vectorization. So this means that when you do operations in NumPy arrays, you will do always operations that operate over the whole array. In this case, if you have you're going to just sum two arrays, you just do x plus y, so one line, and which will do many operations. So one, this is called vectorization, opposed to something like C, where you would loop over arrays and do the sums element by element. Another thing in NumPy is it has all these functionalities to work with the arrays, and yeah, this is how you're meant to use. I mean, to work with NumPy is using this functionality. There are a group of functions that are called universal functions, or ufuncs, that are functions like this one that operate over the whole array. For instance, npexp if you have an array, you apply it, and it will give you an array of the same size that where all the operation has been applied. And yeah, and there are other functionalities, like for instance, vector product, matrix product, matrix product, that are not really of function because it gives something of a different size. But yeah, the NumPy arrays within NumPy, they are meant to be used like that. And another important point, the last important point, is that sometimes the problems are not very easily seen written. Solutions, sorry, are not easily written as in vectorial way. And with NumPy, it's very important to use it. So to rewrite your solutions in a vectorized way. To illustrate this part, that is the most important thing of working with NumPy, I want to show you a couple of problems. One is the computation of the Euclidean distance matrix that appears now and then in different problems, like for instance in kernel methods in machine learning. Sometimes you have to compute this matrix. And the idea is, imagine that you have a list of data points that are these ones here, and you have n data points of size 3 I put. And this the operations that we want to see here is we want to get a matrix that has all the combinations of the distances of the Euclidean distance between the two set of vectors. Okay, so the distance between these two will go here. The distance between these two is going to be here, and so on. And so this one geometrically is just the distance between these two points, the Euclidean distance. So this is the first problem, and the second problem is another distance matrix, but in this case uses a different metric. It's called a city block distance matrix. Then instead of the difference of the squares, it uses the difference, the absolute value of the difference. And so if you start with the Euclidean matrix, distance matrix, since we have to get all the combinations, maybe what comes to our mind first is just to loop over the arrays and get get the distances element by element. But this one, if we see the 3 points that I put before, this is not a good implementation. First, because we are not doing operations over the whole array, and yeah, doing loops in Python is really slow. So the whole thing is already a bad implementation. And here we use some NumPy functionality that I mentioned before, but having loops is already too bad. And the last point, we didn't do anything to adapt it to use the 2 points above. So it's not a vectorized way. Implementation, this is just it's not a good thing, and it's something that mostly for the people that come from C or Fortran, we may be tempted to do something like this. Okay, so just to go to find an implementation that go through these 3 points, we can do this one, and this one uses a concept of NumPy that is called broadcasting. That broadcasting is everything that has to do with operations of arrays with different shapes. And so in this case, this line here, if you have never used it, something like this, the idea is that we have our arrays, so the list of data points or list of arrays, and you can see that we're going to do like subtractions. Like we're going to get one in column way and one in a row. So like column. so like transposed, they used to say it better. So one like a column of data points, and another one where the data points are columns, so a row of many columns. And this one in NumPy, what is going to happen is it's going to give a matrix of n by n by the short dimension, so a three-dimensional matrix with all the differences. And now just we do the squares and sum over the last axis, and then we get the metric that we wanted, and then we do the distance matrix. But this implementation, besides, I mean, it has all the good things. We did the vectorized. This is already way better than this one before. But it has a bit of a problem that is we're creating a three-dimensional matrix here that we don't need, because when we sum here at the end, this is going to be n by n. So we have this one. It will involve a lot of memory. So it can be slow, because doing operations with changing a lot of memory is expensive. So we can continue to do another implementation. And in this one, that shows more the point of rewriting the solutions to make it vectorized. We can use this trick that we can rewrite this the Euclidean distance as the dot product of the two differences. And this one in turn, we can write it like this. And the good thing is that in NumPy, each of these terms here, there are functionalities to calculate it. So this one here, the last one that you see has ij. It's just I mean, if this is not clear, you can see later, but it's just a matrix product, X and Y transpose. And these two here, they are basically the same. Just one is II and the other one is JJ. So this one has IJ. So this one is just element by element. And the idea now is these two can be just transposed, which is what we're doing here. And all the combinations IJ can be calculated. If something is not clear, we have time, you can interrupt me and ask.
What is the colon, comma, and p dot new axis doing?
Yeah, this one. So in NumPy, this one is a we put n by 3 vector, right? And we do n by 3 times n by 3, right? And we get an n by 3, okay? No?
Element-wise multiplication?
Yeah. And then we do sum over the last axis. So now we get n.
Okay.
And in NumPy, so depending what is happening, but in this case, it will give you a shape n comma. It's not an n comma 1 or 1 comma n. So there is no notion of if it is like listed like this. It is like a row vector or a column vector. And this one, the only thing that it does is to tell NumPy, like read it as create a new axis. A new axis is like a new dimension, and inside this that is n. Read it as n comma 1. So now you have like a row with all of them are columns, or you can read it as 1 comma n. So now you have the notion of a column vector or a row vector. Is it clear, or at least?
So what? Well, when you said n by 3, is that what object in this problem actually has those dimensions, or is that just a hypothetical example?
Yeah, I just put just to show one is the short dimension and one is the but there's nothing. It's just I say 3 because I wrote 3 here, so it fits. But is it clear?
Yeah, I think so.
Yeah. The idea is like, there is these two are going to be column let's say column vectors, both of them, or row vectors, both of them. And since we have I and Y, we want to get all the combinations. And the way to get the combinations is to sum all the vectors, so all the elements in one with each of the elements of the rest. And that's done by doing the transpose. And the transpose, it needs sometimes to new axes. Okay, we're going to see a notebook now, and maybe I can explain it easier. And yeah, so at the end we can put everything together in this function, and so we just can compute all the terms, and yeah, and we add all of them, and we put an abs here just for the diagonal. It's going to be 0. So in practice, it's going to be like 10 to the minus 12 or something like that. And just to avoid noise, we always put NP apps to get like positive 0. Okay. So now we can see a notebook here. So yeah. So here I just put the 2 implementations. The one I call it Euclidean broadcast that does the thing with the new axis. And I will show you quickly how it works. And this one, Euclidean trick, that uses this trick to rewrite the Euclidean distance. Okay. So here with time, this is the same thing that I wrote in the slides for you later. And just here, let's time it just to have a look. So here we just created random samples, and here we are just timing. It takes time because it's doing an average of time, but with the function. So we see here that Euclidean trick was 52 milliseconds, while Euclidean broadcast is 1.35 seconds. And we're going to see now in a bit why is that, and how it's related to this operation here that creates the multidimensional matrix. And yeah, so very quickly so if the new axis. So if you put here x, maybe. Maybe do that. So if we have this thing here, it has it's just a vector 0, 1, 2, 3, 4, and if we look for shape, it says it's 5, and now if you do x transpose shape, it's just going to be 5, right? It doesn't change at all. So in order to change to be able to do a transpose, this thing cannot be just a vector because there is no concept of transpose for a vector like this in NumPy. So it needs to be a matrix, and to be a matrix, it needs to be just 5, 5, 1. And what we do is to say, take this vector that has all its data, which is this column, times, comma, NP new axis. And now when you look for shape, it is 5, 1, all right? And now we can do transpose, and now it's going to be 1, 5. And what it changed is that now this row, in this case, is going to be like the one row of a matrix, just if you to see like that, or this one is going to be the columns of size 1 vectors in this matrix. That's it.
Excuse me.
Yeah.
If you do the NP dot new axis before the 2 dots, it's doing the same in the transpose.
Yeah.
And another question: how long would it take the Euclidean operation before with loops?
We're going to see later with NumPy, but yeah, it's a ridiculous amount of times, like maybe 20 seconds or something like for this size. That's why I didn't put it. But we will see now one later with a very short, very little data, and you will see how much time it takes. And yeah, finally here, oops. No, because I redefined X. So I have a very nice notebook that I use in the course we teach at CSCS that is about broadcasting, and I will add it to here. And I thought that maybe it should be a good idea to include it now. I'm regretting it, but you can have a look later if you want. So here we check that both implementations give the same. And another way of checking is just to use is close. And you put here a tolerance, and then this is going to give just true if this is true. So you just do if false is in this one. And if it gives false, it means that they are the same. Okay.
Can I ask you a clarifying question that you put a bit of a broader picture? So if you use TensorFlow in a non-compiled fashion, you can use NumPy, vice versa, right? So how is it then? So TensorFlow, I mean, you know, it also stores stuff like images, so like tensors. So if it needs type operations there, well, my question is TensorFlow smarter than NumPy, or do you also, like, if you do these sort of rotations in data stupidly, does it also essentially double the amount of memory that you use? So meaning you can performance, or like if you do that on a GPU, like not the latest one, but the older ones, they have limited memory. So if you do these operations, that could be like your application instead if you do it stupid. Is that?
No. In this case, for instance, if you do a transpose or a new axis or something like that, what is happens is that the data is stays the same. So the numbers, the memory. And it just NumPy changes how it interprets the data. And they had some slides on that, and I just decided to remove it for the presentation. But yeah, the idea is that there is the NumPy array is formed by the data that is like C code, just a block of memory, and a metadata. And the metadata says there the shape of this data and the strides to see how to read it, and the types, these kind of things. So operations that can be explained with the same memory, like the transpose, that is just change how it is read. They are done without changing memory. And here it's just not really related to NumPy, but I want to show you this app that is called this package is called Linear Profiler, and so you load it like this, and then you do LP run, and you pass the code that you want to run, and you pass the function that you want to profile, and it gives you a line by line breakdown of the compute time of your code. And very nicely here it gives you the percentage, and we see here that these operations, which is element by element, they are around 1% of the time of the runtime, and this one that creates a two-dimensional array, and it's a bit more complex actually. It just goes to 30%, and in here finally just adding the whole thing is what takes more time. That would be not too intuitive to see it like that. And something else that I want to show you here is sorry. a similar package that is called memory profiler, and we can see the memory of usage of both implementations. And here we see the Euclidean trick. It gives you again the memory, in this case, line by line. And here we have the memory at the beginning, so at the point where the function is called. And so you see here how little memory this thing is used compared to these two operations here, which really also explains how this is so fast. Remember that this was around 1% of the runtime. And now if we look at the Euclidean broadcast, here we see that the increasing memory of this operation that creates a three-dimensional matrix is 1.5 gigabytes compared to the whole one here that was 120 megabytes. Sorry, not 120, around 60 megabytes because you already said it. And this is just for the amount of data that we put. If you want to do this operation, for more data, this increase memory is going to be even more dramatic. And it really explains, you can really see clearly here how this operation, even if this is just subtracting numbers, it gets so slow, and this implementation is really quite slow. And yeah.
Sorry, just a quick question. So to run this, I need some packages that are not necessarily part of the setup.
Yeah,
Like the baseline sync IO.
Yeah, it's something called memory profiler and line profiler use.
Those are installed, but somehow might find that. But you say in principle it should be just all standard packages.
Well, they're not a standard like a standard of Python. Same for NumPy. They are external packages of Python. Yeah.
I can download the requirements. It's a mover of.
Okay.
I can export that and then you just take it.
I thought everybody could use the same.
And you can do that, but like if you want to have it on this.
Exactly.
Okay. So, I hope this was clear. I think I should have explained a bit more, but given the amount of time, I guess I did some bad choices on what to explain. But I hope you remember that the main point here that to work with packages, NumPy-like packages like NumPy, CuPy, TensorFlow, PyTorch, the main idea is to use vectorization. And vectorization again means doing the operations over the whole data, over the whole array, and never do loops. Okay. And now we are going to see one of the examples how slow the loops are. Okay, so we had the Euclidean matrix, and we can continue our examples. And the CT-BLUE distance matrix, which uses this metric, it has a problem that the trick that we used before, we cannot apply it because it was based on the particular expression of the Euclidean matrix that has of the Euclidean metric that has this square thing. So that trick we cannot use here, and we can use the one with the broadcasting, but because at the end we get we can get the differences in the same way, which is the more important part. But we know now that it's a bit slow, so maybe we can find different solutions. And for that, we can see the next group of codes in Python for HPC, which is compiled code. And we're going to have a look only to Numba. Numba, I saw that you saw it briefly on Monday, but I guess the point was not to show Numba. But yeah, the idea of Numba is that it has you write Python code, and now you will write it very explicitly with loops, like if it was C. And then it has a just-in-time JIT, a just-in-time compiler that translate just Python code into machine code using the LLVM compilers. And yeah, it's pretty cool because you just write very simple code and decorate it and get performant code. And you can use it with NumPy. And I don't know how much it can be used with other packages NumPy like, but with NumPy you can use it, and it also has support for GPU. For generating GPU code, but it can be a bit complicated to write. And also it supports both NVIDIA and ROCm drivers. And the idea is something as simple as this. You have a vector, a NumPy array, and you want to get the sum of all the elements. And of course, you would do it with NumPy, but to show the example, with NumPy, you will do the opposite as you would do in NumPy. You will just write everything with loops, so NumPy understands what to do. And then you import NumPy and decorate it with numba.git. And there are different ways of NumPy compiles and generates the code. But in practice, you will be using something called NoPython equals true, the NoPython mode. That if there are like Python specific idioms like I don't know, like list comprehension inside of your code, or maybe operations with lists, the NumPy can tell you, yeah, this I won't support it, and you can write it in Python mode, but this one is not going to be too performant. But in practice, I think through the years, NumPy keeps supporting many NumPy functionalities. So now it's very hard to find some of these errors that it tells you this is not supported in Python mode. But yeah, this is basically the idea.
So Python in principle native only runs on one CPU by construction. So NumPy also allows you to do shared memory conversation, right?
Yeah,
so if you just don't have a GPU or if you have 16 CPUs, this will allow you to use efficiently 16 CPUs.
Yeah. We can see an example now with that.
What does JIT stand for?
Just-in-time compiler. Just-in-time.
Okay, so you're calling the just-in-time compiler and you're telling it it's not Python?
Yeah, I will show you the example now, and you will see.
Can I ask you?
Sure.
So you have to export also the number of threads from that? Can you show that too?
We can try here, but I don't know if. Yeah, let's see that we do export. Sorry, it's the next notebook. It's the next. This one doesn't have anything parallel. Okay, sorry. Yeah. Okay, so here we have. We are going to do implementation of the city block, which is the same as we see before, but there is no square of the difference. It's just absolute value. Can you see what the size of that? And so this is just pure Python that we know that this shouldn't be done. Okay. And so the next one, we have just the same thing that we added the just-in-time compiler decorator. And here we put the city block broadcast just for comparison. And here at the end, we do apps instead of the square. Okay. So what is going to happen here is now when we run it, here we're just checking that they all give the same result. But here, what is going to happen is that when this one is run, NumPy, it will generate code based on what of the function is decorated. It's going to compile it, and this compiled code is going to be cached. So then this means that the first time that you run it, there will be a lot of overhead in compilation and generation of code. But from the next time on, the code already exists, so it's going to be it's cached and it's reused, so it's going to be faster. Okay. And that was clear. Yeah. And then here, so we can compare the Python implementations. I put 200 here and 225, the size of the data, because this one is very slow. So this one for 200 is, you see, is 1.16 seconds. Before we were running 2000. While Numba is, yes, 0.8 milliseconds, 100 microseconds. And this one you got it for free just by adding this decorator. And yeah, and here we can compare it with broadcast, with our other idea of implementation. And here we can see which one does better. So here I put more points. Okay, so we have 180 milliseconds compared to Euclidean broadcast is 1.3 seconds. Okay, so now by using Numba compared to the broadcast implementation, we're doing much better. Okay, if this one was the
yeah. This is also a bit of a design question. So, like, if you want to use loops or vectorization.
To me, I don't know. In this problem, I don't know. I don't know. I wouldn't see it like that. I would see it more. I would. I don't know. I imagine that.
No, like, would you do a loop? Inside the loop, you have a NumPy array and you access the individual elements, and then you put on top of that number.
Yeah.
So that's not like hubris. It's fine.
Yeah, it's how it's meant to be used. Sorry, maybe don't.
No, I mean, no.
Okay. Yeah.
No,
Is there a downside to
I
this?
guess we're going to ask if you vectorize, is there any advantage of using number in addition? So putting number on the vectorized code. So you have a completely vectorized code.
Okay, sorry. With no loops. Yeah, no. I think it wouldn't make a difference because, yeah.
So, no, yes. So if you have vectorized code in NumPy, typically still runs in single processing mode, right?
Not necessarily.
No?
Not necessarily. Well, it depends. For instance, the add operation, it is multi-threaded. Some are multi-threaded, some are not. Most of them, they are not, but no, but yeah, whatever is running, because, so if you, oh, what happened? You're still seeing my screen. Sorry, I got, okay. Yeah, when you run a NumPy function, you're just calling something that has already been precompiled in C, and then just adding the Numba decorator is not going to modify it at all. So Numba will only generate code from, like, let's say, traditional, loops and things that it can work with.
I didn't get why Numba is faster than the vectorized Python code. Or did I misunderstand?
So
if Numba does the vectorization, why is it faster than vectorization done by yourself?
Yeah, it's the same thing as before, that we have two different vectorized implementations, and one was faster than the other one. And I think the issue here is exactly the same. It's that when we compute this three-dimensional matrix, because this one, we are getting n by n. So in this case, like 2000 by 2000 by 50. So this one involves a lot of memory. And writing all this memory, it's just expensive. And it looks like when Numba, the codes that generates from this way that we wrote it, it's faster. I think if we wrote something like by hand, we create a very huge matrix and then some afterwards and decorate it with number, it would be slow as well.
So if you do it in Fortran, it would still be much faster. Would you write a Fortran program and write a Fortran program?
I don't know, because the thing is that so Numba doesn't stop there. I will stop there, but Numba also you can do like more specialized things. Like you can declare types of Python, and you can tell it don't check boundaries of arrays, and then you can really strip down all the Python thing and make it very fast. But yeah, maybe you have probably more control in the general code, I guess, with Fortran. Yeah, sorry.
Are there any common like mistakes or things people do that would make number not work? I mean, I think you can't just add it and it will always work. So that it's easy to change.
What do you mean, like crash or not be fast at all?
Like that it won't literally crash.
Yes, there is first this issue with the no Python true, which for another presentation of this that I prepared, I was trying to make it crash myself and didn't manage. But I remember using it and seeing it crash and saying this is not supported in non-Python mode. But yeah, I guess you can make it crash. But I think nowadays it's Numba is very robust. Sorry.
So these things you just discussed, you strip down certain checks and so on to make it faster. That happens during the compilation, or it does that in the machine?
That happens, yeah, during compilation.
So it's then the JIT, the just in time, is the only way, right? You can't just compile the code and then it's compiled and then you run the compiled code because it's faster. It will always just be compiled every time you call it. Or...
No, it will be compiled the first time you call it,
okay.
And then it will be cached, and then the next times it will use the cache machine code.
Just a practical question. What's the trade-off if you think in loops, or you're more comfortable in loops, or you're having a hard time to translate it in vectorization? Is it always going to be, or it's going to be way faster to use this package, which is going to precompile, and it's going to efficiently?
I think in general you have to try. I don't know. For my case, for instance, it is most about sometimes not finding a way to write it in something that already exists. Like for instance, well, this is a bit exaggerated example, but you wouldn't write a neural network training in Numba because you already have it in TensorFlow. Sometimes it's hard to write it even in Numba, even if you use very simple loops, and so sometimes it's just hard to write it, and sometimes it's not really about this one. Maybe it's faster, maybe it's just very hard, and already it's implemented in NumPy or PyTorch or whatever. And
there is something. If you have multiple loops or something that can make the precompilation too slow.
I don't know. Yeah, it would have to be a really, really, really long code to make the compilation slow.
I was just curious, like, what is the downside to using Numba? Because like I feel like if you're somebody who just doesn't want to spend the time to vectorize your code, like it just almost seems like a cheat, right? It's like,
I think it's what I was saying before, that sometimes it's just hard. It's not easy to. Sometimes the algorithm is just impossible to follow, and it's better you use something that is already written in another package than just going over with Numba.
but then if it already exists in the other package, then you wouldn't have to actually write the vectorized code, right?
Yeah, exactly. But it depends how, like for instance, in this Euclidean trick, the matrix multiplication is already written, but maybe you need to do a part of it, or you can have partial help. And okay, so Yeah, I have another example here that it has this one. Ah, no, sorry. I have another example here that it has something new, that is the parallelization capabilities. That was what you were asking before. That here, together with no Python, that we can compress it in ngit, which means JIT in no Python mode. We can pass parallel through, and this one, when you use this this way, this context this option parallel through. So you're telling Numba that you're going to, you know that you want it to parallelize what is inside, and it doesn't do it completely for free. Instead, it gives this function here, p-range, which is like range, but it's called parallel range. And the idea is that it will just parallelize in the loop where you're using p-range. And yeah.
So in open, you have some, you can give essentially the density loop, so you have a chicken loop, just to all to one parallel, and then you can give like arguments here, don't you have an example, and then you know, like essentially, does that, you don't need to tell it exactly parallelize, but then it undoes it automatically.
No, it's not that you don't have too much control. So it's mostly because, for instance, in OpenMP, sometimes you have to tell not everything is private, or this one I want it not to. In this case, I think it can guess from the code, but as I understand, in general, you can use it when you are sure that what you're writing is thread safe. In this case, for instance, I put it here in the outermost loop, and at the end, inside we have we're calculating the distance at this how's it called? It's reducing, accumulating in R. So, but all of them, they are going to be, all these sums are going to be in the same thread. So in this case, it should be fine. They're independent. But in this case, in general, it shouldn't matter where you put it. I guess, because yeah, I think that there is no problem with the order of the accumulation, but I might. Is it clear?
Yeah, but this is exactly the typical example you would see racing conditions in OpenMP.
Yeah, if you do it wrong. Yeah, I have the same example also in C, and I remember I struggling a bit, like changing it here, putting it there, and why? Yeah. And so this one, yeah, it can be a bit. So you have to. It's not really complex, to be honest, compared to OpenMP, because it will do many things for you. But yeah, as Simon said, you don't have enough, all the control you will have in C in this case. But okay, but yeah, the idea in this case is that the first loop we're going to do it with using p-range, which means that it will parallelize in this loop. So for I equals 0, it will do the rest in one thread and the next one in one thread and so on. And here we again check that they both give the same value, and it's 0. And again, here when we run it the first time, this thing got the code got generated and compiled. It's really good. And now, if we sum here, yeah. Is more than half speed up, and in this case just by doing parallelization, which of course this was in this case. It depends how parallelizable is the code that you want to run. You may get different performance, but yeah, the main point here is that you can get yeah, you can get very good speed up again almost for free by using number p-range.
Sorry for being nice. So like what you can do in practice if you were to use a notebook and not plugging what you would just do, as you tried before, you would do like exclamation mark 1P number threads equal the number of.
Yeah, I think
And
so.
would it be physical cores that you would choose threads or the number of virtual cores?
I think it's the number of virtual cores. Yeah.
Where did you choose that? Did you choose that?
Sorry?
Where did you tell it how?
No, I have it now as default. Yeah.
Okay. But you have to tell it somehow.
Yeah, normally I always put it when I write a kernel for an installation. I just put it there and
So how many did you put? To understand the speed up.
yeah. In this case, for instance, I guess we can do like this: export. I think we have like 16.
No, you have 4. So you have that.
That's all the rest of the numbers, no?
I mean, I didn't crank it up in 4.
No, I think no, 16.
You have 16?
Yeah, unless.
I gave the students 4.
But anyway, yeah, I don't know if in a notebook, I always forget if this is just going to create it like a launch in a different environment or in the same environment of the notebook. So that's how I always put it, set it before I launch the notebook or in the kernel. But anyway, we are I'm really sorry over time.
Oh, no, you're fine. You have more time.
Okay, thanks.
You're not stop yet.
Okay, so
18 minutes.
yeah, okay, and just here quickly, as I was mentioning, so in the arguments of JIT, there are many other specializations that you can put. You can even specify how you want it to compile, or if you want to link the code to a particular library, and you have a lot of freedom in that. Yeah, in that sense. And there are things like this one, for instance, just a second. For instance, that this is fast math true is an option of the LLVM compilers, and it does really a bunch of optimizations and can ruin your code actually.
But this is like the Fortran compiler minus fast math compiler.
Yeah, it's something like that. But I was reading that they had historically many different optimizations levels and different properties options, and they sort of group all of them in fast math.
Really nasty. It's like -03, minus.
Yeah, something like that. Yeah, but they recommended to use it. I guess you have to try, but in cases that precision is not particularly important, or the parallelization is not like it's really thread safe, you can use it. Otherwise, it can really ruin your. But in this case, for instance, it gives us the same result. We see 0 here, and before it took 71 milliseconds for this data, and now if we run it again, it drops down to 25 milliseconds, which is really good. But again, this one is to be tempting, but it should be treated with care.
I have a question.
Sure.
I work in MATLAB, so this is Python is new for me. If I want to have the help file of Numba, is that available, or like that systematically describes all these options, for example?
There is this here. Wow.
And then related question is when do you tell them that the Numba is over? Like they see no end, or
Now, in general, you decorate a function.
Stupid question. Like you make all these loops, but there is no end. Like how does the code know that it's over?
Yeah, because in Python you have the indentation. And so if
yeah, okay, yeah, got it.
yeah, if you have something here, the code finish here in this return.
Thanks.
And yeah, these packages that are very popular, like the ones I have mentioned, they really tend to have very good documentation. So if you want the help
on the internet, like
Yeah,
Google,
yeah.
Numba help?
Yeah, in general, you can find things. My example was not too good, but like, let's see, with this one, in this case, it can give you like a basic documentation of the function, but in general, I think it's better to go to the documentation and find stuff.
Yeah.
Yes.
So now that you already compiled it the first time, if you run it again a little bit faster, would it be the same speed independent of whether you use FastMath?
Yeah, let's give it a try. I will delete this because now it's too fast. But and let's run it for the first time. I use time, and then we do like this. No, X. Ah. Sorry. So here it took 477 milliseconds. So it's the first time. And now when it runs again, it's 20 milliseconds. Okay, yeah, I'm sorry for being over time. I want to show you only one thing to finish, and we finish. Okay, so I have 10 minutes.
Yeah, roughly. You're the last of the day, so we can be a bit generous.
Okay, I'm sorry. So the last thing, the last group is about scaling. That I think this one may be maybe the most important, or more, the one that you may use more. Here there are a few examples, but I want to show you Dask. That is a very popular one. And the idea of Dask, it has two different components. One is like a queue kind of thing that you can create, and you can put tasks, operations, and then it will schedule it. And you can schedule it in threads in your laptop, and you can schedule it in a supercomputer using multiple nodes. This thing has been used as backend for many other projects, many in machine learning, for instance, to do distribution. And so there are this part, and on top of it, it builds three different data collections and operations with it. That is, it implements pandas in a block algorithm way that can be it can be scaled. It implements NumPy and implements some sort of a list thing to like a scalable list for clusters. And the first part, the queue component part, it works like this. So let's say that you have this code in Python, and you want to make it let's say parallelize it in with Dask, and parallelize it can be again running it in multiple threads in your laptop, or running it in multiple machines. Okay, so what you do is you get these functions, and you wrap it with Dask delay, and this one, when you run it, it will just run immediately, and it will create a graph, and it is smart, like to know, like for instance, that these two operations they can be executed at the same time because they don't depend on each other. And said it knows that it depends on the result of x and y, because x and y. So it will create the graph accordingly, and then you can do set.compute, and it will run the whole graph. And also you can create like list of tasks and then run them, and things like that. Yeah.
So how do I, so like typically, you know, like if you say you can run on multiple computers, so like is this a sort of text, if it has a hybrid environment, like, you know, it's a different, for me mentally, it's difficult to have a shared memory parallelization. They run copy of the data, you can work on that, but you have multiple, you know,
like processes and threads.
Yes, so does it automatically swap between processes?
No, I think you can specify, like here that I put threads, you also can specify if you say processes, it will just copy all the memory and create Python processes with different memory. What was the question? Or?
Yeah.
And yeah, just to code quickly, this is the other part that I mentioned. There's implementation of other packages, but in a parallelizable way, and this is built in on this delay thing. And I can show you quickly a notebook. So you see this one, how it works in practice. Yeah. So here we have these two functions, and so this one is squares n, and this one sums to numbers, and I put the time slip 2 seconds, so they take some time. So if we run it here, this is going to be it's going to take 6 seconds because it's 2, 2, and 2. But we can parallelize it with tasks using threads, for instance. And for that, what we do is we wrap everything, as I mentioned before, with dash delay. And now we can visualize. And you see it does the 2 squares, which is this function. Is the first thing that we did, and then at the end it adds the two final numbers. And one important thing in Dask is that it will just run things one after the other one. It won't try to force parallelization or anything. And what I mean with that is that, for instance, here this visualization is shown with colors and with numbers. Which operations are going to run one after the other one. Like for instance, these two, it will run first this orange, so the square, and then the other square. And they are only going to be run in parallel, in the case of threads, for instance, if the function that is run inside, so in this case, this function here, it will release the lock mechanism that Python has to avoid multi-threading. And in this case, time does it. So time is allowed to run in Python in multiple threads. But other functions that they cannot run in multiple threads, Dask is going to run them one after the other one. So it will just start running. And if they can run in threads, okay. If not, they have to wait. And sometimes there can be cases that you do something like this in Dask using threads, and then you see, okay, this is just even worse because now you have the overhead of scheduling. And it can be because your function is not allowed to run in multiple threads. And here, when we compute here, at the end, so just at this point, there is no computation. We get 5 point. I think I don't know. That shouldn't be 5 seconds. I might probably I don't know. There is something probably slow in the building the graph for the first time, but I guess depending on the system. But now you see that it is 4 seconds instead of 6 because these two they will run at the same time. And yeah, I have another notebook that I won't show because I am too over time. But we do an implementation similar like this to compute the city block distance matrix with Dask. And the idea is that we split by parts the computation and then put it all together and give it to Dask. So Dask it will run in parallel all these splits, and we're going to get a good speed up. You can have a look here. You can have a look here, and if you have questions or something, you can always write to me and we can discuss. And the main point, one very important point here is that again that here we use threads, but we can use a different backend of Dask that we can run this graph if it was something more complicated, we can run it in multiple machines or using processes or in different ways.
But so you cannot mix threads and processes.
No.
So it's either or, it's like hardcore MPI or hardcore in classical sense.
Well, you can, because you cannot do with Dask. You cannot use processes for this and tell threads for that, but you can run with processes a function like if this.
You would do like.
Yeah, if this square uses already multiple threads, Dask doesn't care.
Okay, so you would, for instance, combine that with your loom basing, for instance, you have a loop.
Yeah.
Dask around.
Exactly. And then you would set, I don't know, you run it in 4 threads, and you tell OpenMP num threads equal 4 in this case, and Dask is going to run it, and it's up to what you're running to use the threads or not. And just to close, I hope this was useful. Was really fast. I apologize for that, but just try to the take home is that NumPy like code, TensorFlow, PyTorch, these kind of things, they use us to go for vectorization and avoid loops and just always rewrite everything in a vectorized way. And then if that doesn't work, you can always go and try Numba. And that is very, very simple. And there are other options like Cython, but Cython, you really need to learn a particular syntax of Cython that is more complicated. And then you can, if you need to scale, or like scale can be like from one core to multiple cores, or from one computer to multiple computers. You can always go with this Dask delayed, and it's just 3 methods that for free you can get a lot of functionality, and you can use in your daily work. And again, I apologize for being so over time, and thank you for your attention.